In this video, we're going to learn the product property of radicals. The product property of radicals is a very important property that helps us to simplify radicals. We'll use this property throughout the rest of the chapter. We will also learn the quotient property of radicals. The product property of radicals says that if you multiply two radicals that have the same index, you can combine that multiplication underneath one radical symbol. And with the product property of radicals, you can go in either direction. If you're multiplying two radicals with the same index, you can combine that multiplication underneath one radical symbol, or you can go in the reverse direction. If you're multiplying two quantities underneath one radical, you can break that multiplication apart into two separate radicals. Let's look at some examples. In order to use the product property of radicals, the radicals that you're multiplying must have the same index. Since these are both square roots, they have the same index, so the product property of radicals says we can combine that multiplication underneath one square root symbol, which would give us the square root of 5 times 3, which simplifies to the square root of 15. Let's look at another example. Since we're multiplying two radicals that both have the same index, which is 4 in this case, the product property of radicals says we can multiply these two quantities underneath one radical symbol, which would give us the fourth root of 7 times 11. And if we simplify that, 7 times 11 will give us the fourth root of 77. For this example here, since we're multiplying two radicals with the same index, we can multiply these two quantities underneath one radical symbol, which would give us the fifth root of 7a cubed times 3a. And now if we multiply these two quantities together, you want to multiply like quantities. So we'll multiply the numbers. 7 times 3 will give us 21, and we'll multiply the a's. And when we multiply a cubed times a, we keep the base, which is a, and we add the exponents. So 3 plus this implied exponent 1 will give us 4. Lastly, for problem number 4 here, this is the cubed root and this is the fourth root. So these two radicals have different indices. If you're multiplying radicals that have a different index, you can't use the product property of radicals. So far in chapter 6, all of the radicals that we've simplified have had radicands that are perfect powers. For example, we've simplified the square root of 36. Since the implied index here is a 2, we want to rewrite 36 as some quantity squared. We can rewrite 36 as 6 squared. So the square root and the square exponent are inverse operations. They cancel each other out. So the square root cancels the square, and all that we're left with is 6. So we call 36 a perfect power. More specifically, it's a perfect square. So this problem worked out perfectly because we needed to rewrite 36 as a perfect square, and we were able to. We've seen this problem as well, the cubed root of 8. Since this is the cubed root, we want to rewrite 8 as some quantity cubed, and we can. 8 can be written as 2 cubed. Now these match, and the cubed root and the cubed power are inverse operations. So the cubed root cancels the cubed power, and we're just left with 2. So this problem worked out perfectly as well because 8 is a perfect power. More specifically, it's a perfect cube, which was great because we needed to write 8 as some quantity cubed so that the cubed root and the cubed power would cancel. So all of the problems we've seen so far have involved perfect powers, which made simplifying work out really nicely. But the next step is, what if you want to simplify a radical like this? The implied index, which I'll write here, is a 2. So to use this strategy to simplify, we want to rewrite 24 as some quantity squared, because then the square root and the square power will cancel. But 24 cannot be written as some whole number squared. 24 is not a perfect square. So the question is, how do we simplify a problem like this? And that's what we'll learn next. Before we learn how to simplify the square root of 24, we're going to make a list of perfect squares, perfect cubes, and perfect fourths, because we'll need to be very familiar with these in order to simplify. A perfect square is any number that can be written as some quantity squared. So for example, 1 is a perfect square because we can write 1 as 1 squared. 4 is also a perfect square because we can write 4 as 2 squared. 9 is also a perfect square because we can write 9 as 3 squared. And I've continued listing our perfect squares here. We could go on indefinitely, but this gives you a good idea of some of the most common perfect squares that you'll see. Next, let's list some examples of perfect cubes. A perfect cube is any number that can be written as some quantity cubed. So 1 is a perfect cube because we can write 1 as 1 cubed. 8 is a perfect cube because we can write 8 as 2 cubed. 27 is the next perfect cube because we can write 27 as 3 cubed. And here's a list of several more perfect cubes. Last, a perfect fourth power is a number that can be written as some quantity to the fourth. So 1 is a perfect fourth power because it can be written as 1 to the fourth. 16 is a perfect fourth power because it can be written as 2 to the fourth. 81 is a perfect fourth power because it can be written as 3 to the fourth. And I've continued listing several examples of perfect fourth powers. Now we're going to refer back to this list many times throughout the rest of the chapter. Now let's revisit this problem. We're asked to simplify the square root of 24. Again, the strategy that we learned in 6.1 is that since the implied index here is a 2, we want to rewrite 24 as some quantity squared, because then the square root and the square will cancel and we'll have our answer. But 24 is not a perfect square. You cannot rewrite 24 as some whole number squared. 24 is not a perfect square. So we need to find the largest perfect square that multiplies evenly into 24. So let's look at our list of perfect squares. And again, the reason we're looking for perfect squares is because the index here is a 2. If the index was a 3, then we'd be looking for perfect cubes. And since 24 is not a perfect square, we need to find the largest perfect square that multiplies evenly into 24. To do that, let's look at our list of perfect squares, and we want to find the number as close to 24 as we can get, but it has to be less than 24 if it's going to multiply into 24. So the largest perfect square that I can find that's less than 24 is 16. If you take 24 divided by 16, you get a decimal. So that means that 16 doesn't multiply evenly into 24. Let's keep working from the largest numbers down. Does 9 multiply evenly into 24? No, because 24 divided by 9 gives us a decimal. Okay, we're trying to find the largest number, so we're working from the largest numbers down. Does 4 multiply evenly into 24? Yes, because 24 divided by 4 gives us 6, a nice whole number. So 4 is the largest perfect square that multiplies evenly into 24. So now I'm going to start by copying down this original problem right here. We want to rewrite 24 as 4 times some number. So let's see, 24 could be written as 4 times 6. So now we've created an equivalent problem. 4 times 6 is equal to 24, but we've rewritten 24 using the largest perfect square that multiplies into it. Now, let's look back at the product property of radicals. Remember, the product property of radicals goes in both directions. It says if you multiply two radicals that have the same index, you can combine that multiplication underneath one radical. But the product property of radicals also works in the reverse direction. If you're multiplying two quantities underneath a radical symbol, you can break those quantities apart into two separate radicals. And that's exactly what we're going to do in our current problem. Since we're multiplying two quantities underneath one radical symbol, let's break that apart into two separate radicals. Now we want to simplify each radical. 4 is a perfect square, so this is going to simplify to a nice whole number. The square root of 4 gives us 2. So we pulled the largest perfect square out of 24 that we could. 4 was the largest perfect square, and the square root of 4 gave us 2. Now 6 is not a perfect square. That's just what was left over after we pulled out the largest perfect square that we could. So we're going to just keep bringing down the square root of 6. That can't be simplified any further. So we've now simplified the square root of 24 to get 2 square root of 6. These are equivalent. If you type the square root of 24 into your calculator, you'll get approximately 4.9. If you type in 2 square root of 6 into your calculator, you'll get the exact same decimal, approximately 4.9. So when we're simplifying square roots, first check to see if your number is a perfect square. If it's not, you want to pull out the largest perfect square that you can from that radical. Now, instead of the square root of 24, We're now going to simplify the cubed root of 24. So since this is a cubed root, first we want to check to see, can we rewrite 24 as some quantity cubed? Because if we can, then the cubed root and the cubed power will cancel, but we can't. No whole number cubed gives us 24. You can see this in two ways. If you type the cubed root of 24 into your calculator, you'll get a decimal. Or if you look at our list of perfect cubes, you'll see that 24 is not on that list. So let's start by saying that 24 is not a perfect cube. We need to find the largest perfect cube that multiplies evenly into 24. Let's look back at the chart we made on page 2, and we're looking for perfect cubes. So we're going to look at this column here. We need to find the largest perfect cube that multiplies into 24. So we need to start with the largest number we can find that's less than 24, because in order to multiply into 24, it has to be less than 24. The largest number I can find that's less than 24 on our list of perfect cubes is 8. Does 8 multiply evenly into 24? Yes, it does. So 8 is the largest perfect cube that multiplies evenly into 24. So I'm going to start by copying down our original problem here. We need to rewrite 24 as 8 times some number. 8 times 3 gives us 24. So now we've written an equivalent expression, but we wrote it this way because we needed to identify and separate out the largest perfect cube that multiplies into 24. Now we're going to use the product property of radicals. The product property of radicals says if you multiply two quantities underneath one radical symbol, you can break that multiplication apart into two separate radicals. Now we know that 8 is a perfect cube, so this will simplify to a nice whole number. So since the index here is a 3, we want to rewrite 8 as some quantity cubed. 8 can be written as 2 cubed, and then let's bring this radical down here. Now, the cubed root and the cubed power are inverse operations. They cancel each other out, and we're just left with 2. And the cubed root of 3 is the leftover after we pulled our largest perfect cube out of 24. So this we're just going to carry down to our final answer. So the cubed root of 24 is equivalent to 2 times the cubed root of 3, but this is considered the simplified form, since for this form we've pulled the largest perfect cube that we could out of 24. Now this approach will work for all of the problems that we'll see in this section, but our problems are going to get more and more complicated, so I'm going to show you a condensed notation that is especially helpful when we get to the more complicated problems. When we're using the condensed notation, we start off the same way. Now, for the condensed notation, we don't bother breaking this apart into two separate radicals. With the condensed notation, we just keep it together underneath one radical symbol. But as we did over here, we rewrote 8 as 2 cubed. We want to do the same with the condensed notation. So 8 is a perfect cube, and we want to write it as 2 cubed, because then the cubed root and the cube power will cancel. 3 was not a perfect cube, it was just the leftover after we pulled out the largest perfect cube, so we just keep the 3 as is. Now, if we broke this apart into two separate radicals, we'd have this exact same step over here. But with the condensed notation, we just keep it all written underneath one radical. Now remember, the cubed root and the cube power are inverse operations. They cancel each other out. So when we're looking at this 2, the cubed root on the 2 will cancel the cubed power on the 2, and we'll just be left with 2. Another way to think about it is, since we're dealing with a cubed root, anything that has a cubed power underneath the radical, you can pull out of the radical. So we're going to pull the 2 out of the radical. Now the 3 does not have a cubed exponent to cancel this cubed root. So there's no canceling that we'll be doing for this 3. The 3 stays underneath the cubed root. And notice we end up with the same exact answer that we did over here. Both of these approaches work, but again, when the problems get more and more complicated, this condensed notation will save you several steps. We'll keep practicing both notations. For this problem here, since the index is a 4, we start by asking ourselves, can we rewrite 26 as some quantity to the 4th? Because then the 4th root and the 4th power will cancel. But we cannot. There's no whole number that when raised to the 4th gives us 26. If you look at our list of perfect fourths, you will not see 26 on that list. So since 26 is not a perfect 4th power, We need to find the largest perfect fourth power that multiplies evenly into 26. So let's look back at our chart of perfect fourth powers. So let's find the largest number that we can that's less than 26. That would be 16. Does 16 multiply evenly into 26? No, because 26 divided by 16 gives us a decimal. So the only perfect fourth power that multiplies evenly into 26 is 1. So if here the largest perfect fourth power that multiplies evenly into 26 is 1, that means that your radical cannot be simplified. Let's take a look at another example. Again, we want to simplify this radical. The first thing you want to ask yourself is, since this is the cubed root, can we rewrite 2048 as some quantity cubed? Because then the cubed root and the cubed power would cancel. But we can't, because 2048 is not a perfect cube. It can't be written as some whole number cubed. So we now need to ask, what is the largest perfect cube that multiplies evenly into 2048? And again, the reason we're looking for perfect cubes is because the index here is a 3. Let's look back at the list we made on page 2, and we're going to look at the perfect cubes column. Let's find what's the largest number on this list that multiplies evenly into 2048. We'll start with this largest number. If we take 2048 divided by 1331, we get an ugly decimal. So let's work our way down. 2048 divided by 1000 is a decimal. 2048 divided by 729 is a decimal. But 2048 divided by 512 is a nice whole number. So it looks like 512 is the largest perfect cube on this list that multiplies into 2048. We need to rewrite 2048 as 512 times some number. 2048 can be written as 512 times 4. Now you'll notice that throughout the rest of the chapter, I'm always going to put the perfect powers in red. I recommend that you do the same in your notes. And if you don't have colored pens, you could instead underline your perfect powers. Now, first I'm going to work through this using the longer notation. After that, I'll show you the condensed notation over here. If we're using the longer approach, next we use the product property of radicals, which says we can break this apart into two separate radicals. Now, this is a perfect cube, so we want to rewrite this as some quantity cube. If we look back at our list here, we see that 512 can be written as 8 cubed. So I'm going to go ahead and write 512 as 8 cubed. Now 4 is not a perfect cube. It was just the leftover after we pulled out the largest perfect cube. We'll just carry the cubed root of 4 down. Now the cubed root and the cubed power are inverse operations. They cancel each other out, and we're just left with 8 cubed root of 4. Next, let's solve this same problem using the condensed notation. It starts off the same way. I'm going to copy this exact same step over here. Now, instead of breaking this apart into two separate radicals, we're going to keep this all written nice and condensed underneath one radical. But just like we did over here, 512 is a perfect cube, so we wanted to rewrite it as 8 cubed. We'll do the same thing over here. Since 512 is our perfect cube, we'll write it again as 8 cubed. 4 was not a perfect cube, it's just the leftover, so we're just going to bring down the 4. Now, anything underneath the radical that has a cubed power to match this cubed root can be pulled out of the radical. So we're going to pull the 8 out of the radical, and that leaves us with 8 outside of the radical. Why can we do that? Because if you focus on the cubed root of 8, the cubed root on the 8 and the cubed power on the 8 are inverse operations. They cancel each other out, and so we're just left with 8. But now I'm going to cover up this. If we just focus on the cubed root of 4, that can't be simplified any further. There's no 3 exponent on the 4 that would cancel the cubed root, so that means the 4 stays underneath the radical. So I've kept the 4 underneath the cubed root. And notice we end up with the same answer here that we did over here. Now, when we were identifying the largest perfect cube that multiplies evenly into 2048, we looked at our list of perfect cubes on page 2. But this list stopped at 1331. We didn't list any perfect cubes higher than that. Luckily, 512 was the largest perfect cube that multiplied into 2048. But what if you're trying to find the largest perfect cube and you find a perfect cube, but what if it's not the largest perfect cube? That can often happen, especially if you're working through a problem very quickly. So this is the question. What if we don't find the largest perfect cube that multiplies evenly into 2048? For example, 64 is a perfect cube that multiplies evenly into 2048, but it's not the largest perfect cube. So what if we solve this problem using 64? Can we still get the right answer in the end? I've started by copying down the original problem here. Now let's suppose we make a mistake here. We don't realize that 512 is the largest perfect cube that multiplies into 2048. We mistakenly think it's 64. I'm going to use the condensed notation here, and so we're going to rewrite 2048 as 64 times some number. And 2048 can be written as 64 times 32. Now, if we're using this condensed notation, we're not going to break this apart into two separate radicals. Instead, we're going to look at our perfect cube in red here, and we want to write it as some quantity q. So you can try a few numbers on your calculator. Try 2 cubed, 3 cubed, 4 cubed. Once you try 4 cubed, you'll see that that's equivalent to 64. You could instead look back at our list of perfect cubes here and see that 64 can be written as 4 cubed. And 32 was the leftover, so we'll bring that down. Now, using the condensed notation, anything underneath the radical that has a 3 for an exponent to match this 3 index, we can pull out of the radical. So we're going to pull out the 4, and that makes the 4 outside of the radical. And now the 32 is still left underneath the cubed root. Now notice these answers don't match, and that's because 64 was not the largest perfect cube. 512 was. But we still can get the correct answer. It's just going to take some more steps. Since 64 was not the largest perfect cube, we're now going to notice that within our answer, there's a perfect cube that multiplies into 32. So what is the largest perfect cube that multiplies evenly into 32? So let's start with the largest number we can find that's less than 32. That would be 27. Does 27 multiply evenly into 32? No. Let's work our way down. Does 8 multiply evenly into 32? Yes. So 8 is the largest perfect cube that multiplies evenly into 32. So I'm going to bring down the 4 and the cubed root symbol, and we now want to rewrite 32 as 8 times some number. We can rewrite 32 as 8 times 4. Here we have a perfect cube underneath our radical, so we need to write it as some quantity cubed. 8 can be written as 2 cubed, and 4 was the leftover, so we'll just bring the 4 down. Now, anything underneath the radical that has a 3 for an exponent to match this 3 index can be pulled out of the radical. So we're going to pull the 2 out of the radical, and we'll bring down the 4. And when we bring the 2 out of the radical, we multiply it by any coefficient that was already there. So we'll multiply this 2 by the 4. If we focus on the cubed root of 4, the 4 does not have a 3 for an exponent. So there's no 3 exponent here to cancel out this cubed root. So this 4 stays underneath the radical, and we're left with the cubed root of 4. And for our final answer, let's multiply 4 times 2 to get 8 cubed root of 4. And we end up with the same answer we did up here. But notice when you identify the largest perfect cube, the problem is much shorter to solve than if you find a perfect cube that's not the largest. Next, we're going to simplify these two problems here. Knowing how to simplify this type of problem will be very helpful in a few chapters when we learn the quadratic formula. So for problem number 9, I'm going to focus all of my attention on this radical here. Let's use the strategies that we just learned to simplify the square root of 63. Since there's no index here, we know that the implied index is at 2. And so the first question we need to ask ourselves is 63 a perfect square? It is not. So since 63 is not a perfect square, we need to ask ourselves, what is the largest perfect square that multiplies evenly into 63? Let's look back at our list on page 2, and we're going to focus on the perfect squares. 9 is the largest perfect square that multiplies evenly into 63. So we're focusing on this radical here, so everything else in the problem I've copied down exactly as it was. And we found that the largest perfect square that multiplies evenly into 63 is 9. So let's rewrite 63 as 9 times some number. And 63 can be written as 9 times 7. And again, 9 is our perfect square, so I'm putting it in red. Now, using the condensed notation that we learned, anything that's a perfect square, we want to write it as some quantity squared. So let's rewrite 9 as 3 squared, and then we'll bring down times 7. Now, since this is a square root, the implied index here is a 2, so anything underneath the radical that has a 2 for an exponent can be pulled out of the radical. So we're going to pull the 3 out of the radical. That will leave us with 6 minus the 3 that we pulled out. 7 will be left underneath the square root, and then we still have 3 in our denominator. Now remember, when you pull the 3 out of the radical, we no longer have this 2 exponent. That's because this 2 exponent was canceled by this square root, just leaving us with 3. Now we've successfully simplified the radical. The square root of 63 can be simplified to 3 square root of 7. But now that we've simplified this radical, we need to focus on this whole fraction here and further simplify the fraction. I'm going to show you 2 methods that can be used to simplify this, but first I'm going to show you 2 of the most common mistakes. A very tempting mistake is that someone will try to take the 6 and subtract the 3. We cannot do that. Don't subtract the 6 minus 3 here. We're actually going to look at this type of situation in much more detail in Chapter 6, Section 4. But let me provide a brief explanation here. If we look at a related example here, since these are not like terms, we cannot take the 6 and subtract 3. Just like these are not like terms, these are also not like terms. These are not like terms because this has x for a base and this does not have x for a base. Similarly, these are not like terms because this has square root of 7 for a base and this does not have square root of 7 for a base. So these are not like terms, they cannot be subtracted. Another very tempting mistake is that someone will want to cancel these 3's, but we cannot do that. The reason being is because we have to recognize that we have 2 terms here. We need to divide the 6 by the 3, and we also need to divide the 3 square root of 7 by 3. If we were to cancel these 3's, we have divided the 3 radical 7 by 3, but we've totally discounted the fact that we also need to divide the 6 by the 3. So please do not cancel these 3's at this point here. Let me show you the correct way to simplify this expression. Method 1, I like to call the splitting method. And method 1 is my favorite approach. For method 1, we're going to split this apart. We can rewrite this as 6 divided by 3, and then we put the minus sign in the middle, and then 3 square root of 7 divided by 3. Splitting it like this allows us to further simplify it. Now we can take 6 divided by 3 to give us 2, and 3 divided by 3 gives us 1, so we're left with 1 square root of 7, or just the square root of 7. So this is our final fully simplified answer. But let's take a look at another possible method we could use to simplify this expression. In method 2, we're going to factor the numerator. Let's look at a similar related example. Let's suppose we're trying to factor this expression here. The GCF here would be 3, so we put the 3 outside of parentheses, and then 3 times 2 will give us 6, and 3 times a negative x will give us our negative 3x. Now, this is the same problem. It's just that we've replaced the x with the square root of 7. But to factor this, we do the same thing. We first look at the coefficients and identify the greatest common factor of these coefficients, which would be 3. We put the 3 outside parentheses, and then we can say 3 times 2 will give us 6. And if we take 3 times a negative square root of 7, that will give us negative 3 square root of 7. This expression is exactly what we have written in our numerator on the previous page. So we just said that we can factor this numerator by factoring out the GCF, which was 3, and that would give us 3 times 2 minus the square root of 7. And let's make sure to carry down our denominator, 3. So now that we've factored, we can cancel, and we can cancel the 3 in the numerator and the 3 in the denominator. And that leaves us with the quantity 2 minus the square root of 7, which is the exact same answer we got using method 1. So you can pick whichever approach you prefer. Let's take a look at one more similar example here. Again, we just want to start by simplifying this radical. This is a square root. So the first question we need to ask is 32 a perfect square? It is not. So since 32 is not a perfect square, what is the largest perfect square that multiplies evenly into 32? Let's look at our list of perfect squares. It looks like 16 is the largest perfect square that multiplies evenly into 32. So let's rewrite 32 as 16 times some number. And we can rewrite 32 as 16 times 2. So now when you're simplifying square roots, anything in red, anything that's a perfect square, you want to rewrite as some quantity squared. And 16 can be written as 4 squared. And then we'll bring down our times 2. Now, since this is a square root, anything underneath the radical that has a 2 for an exponent can be pulled out of the radical. So we're going to pull this 4 out of the radical, and that will leave us with -2 plus the 4 that we pulled out. Underneath the radical, we still have the 2, and then this should be still all over 4. Now, we've simplified the square root of 32 to 4 square root of 2. Now that we've simplified the radical, we need to simplify the fraction. Remember the two most common mistakes. Do not take -2 and add 4. We can think of these as not being like terms. The 4 has square root of 2 as its base, and this number does not have a square root of 2 as its base. So we can't combine these. Also, you cannot cancel these 4s. This is a term and this is a term, and you can't cancel terms or parts of terms. So this 4 is a part of a term. You can't cancel it. If we use method 1 here, that's where we split it. So we're going to split this and write it as -2 divided by 4. We put the plus sign in the middle, and then 4 square root of 2 over 4. Then we simplify each of these quantities separately. -2/4 reduces to -1/2, and if we examine this quantity here, 4 divided by 4 gives us 1. So we're left with 1 square root of 2, or in other words, the square root of 2, giving us this for our final answer. If instead we use method 2, we're going to factor this numerator here. Well, since the first term is negative, we know that our greatest common factor will be negative, and the greatest common factor here would be -2. So we'll factor out the -2. -2 times 1 will give us -2, and -2 times -2 square root of 2 will give us +4 square root of 2. And then we need to write this all over 4. Now, this is in factored form, and we can cancel factors. So if we look at the -2/4, that can be reduced to -1/2. Now, it's good to know that there's two different methods here, because sometimes depending on what method you use, your answer might look slightly different, but they are equivalent. Next, we're going to look at how to simplify radicals that involve variables. I'm first going to solve this the longer way because that's going to help me explain an important concept here, and then we'll look at the condensed way after. Since the implied index here is a 2, that means that we're looking for perfect squares. And we'll look at the number 75 and the variable z² separately. Let's start with 75. The first question we need to ask ourselves is 75 a perfect square? It is not, because no whole number squared gives us 75. So next we need to ask ourselves, what is the largest perfect square that multiplies evenly into 75? 25 is the largest perfect square that multiplies evenly into 75. So we're going to rewrite 75 as 25 times 3. Next, let's look at our variable. And the first question we need to ask is z² a perfect square? Yes, it is. So since z² is a perfect square, I'm going to put it in red. Now, if we're using the longer approach, we're going to use the product property of radicals here, which says when you're multiplying quantities underneath a radical, you can break that apart into separate radicals. So I've broken this apart into 3 separate radicals: the square root of 25 times the square root of 3 times the square root of z². Now we can compute the square root of 25 mentally. That would be 5. The square root of 3 was just the leftover after we pulled out the largest perfect square, 25. So we keep the square root of 3 as is. And then what would the square root of z² simplify to? We're going to have to look a little deeper into this. I'm going to start by copying this exact expression over here. Notice here, the instructions say assume that all variables are greater than or equal to 0. But in this box here, we're going to ask the question, what if we weren't making that assumption? What if all of the variables were not greater than or equal to 0? Well, the square root of 25 would still be 5, and we'd still carry down the square root of 3. But now to simplify the square root of z², we have to remember the rule that we learned in 6.1. And here is our 6.1 worksheet. In 6.1, we learned that when you have an expression like this, where the index matches the exponent, those are inverse operations. They cancel each other out, and we're just left with a. But you have to be very careful here, because if n is even, you have to put absolute value bars around your answer. If n is odd, you do not need absolute value bars around your answer. So here, the implied index is a 2. The index matches the exponent, so they're inverse operations. The square root will cancel the square, and we'll just be left with z. But since this matching number is even, we need to use absolute value bars. So I'm going to put absolute value bars around our answer. Why do we need those absolute value bars? When you square any number, positive or negative, you get a positive result. So this square makes this radicand positive. And if you take the square root of a positive number, you're going to get a positive answer. So these absolute value bars ensure that our answer is positive as it should be. And the typical way to write your answer here would be to put the 5 first, then we'll put the variable, the absolute value of z, and we put the radical last. So I'm going to put the square root of 3 at the end. So if your variables might be positive or negative, when you're using this rule where these two numbers match and cancel, if this matching number is even, make sure to put absolute value bars around your variable after canceling them out. But from here on out, in this section and throughout the rest of chapter 6, we're going to see the instructions that we may assume that all variables are greater than or equal to 0. A lot of times in the real world, our variables are greater than or equal to 0 anyway, so this is often a safe assumption to make. And when we're allowed to assume that all variables are greater than or equal to 0, that makes our lives easier. Because if we're assuming that all variables are greater than or equal to 0, then we don't need absolute value bars, because absolute value bars make quantities positive, and they would only be redundant because we're told our variables are positive anyway. So if we look back at the original problem, when we're simplifying this expression here, the square root cancels the square, and we're just left with z. And when you see these instructions that you may assume that all variables are greater than or equal to 0, you don't have to worry about using absolute value bars because we're told that z is positive anyway. And absolute value bars make your quantity positive, so that would be redundant since we know this is positive anyway. And again, when we write our final answer, we typically write the radical last. So I'm going to put the 5z first, and then the square root of 3. Now, I'm going to quickly do this problem using the condensed notation because as the problems get more and more complicated, the condensed notation allows us to get the answer in less steps. I started by copying down the original problem, and we're going to start off with the same exact first step. So I'm going to copy this first step down here. With the condensed notation, we don't break these pieces apart into separate radicals. Instead, when we use the condensed notation, anything that's a perfect square, we need to write it as some quantity squared. So 25 we can write as 5 squared. 3 is not a perfect square, so we just leave it as is. And z squared is a perfect square, but it's already perfectly written as some quantity squared, z squared. So we'll just leave it as is. Now, again, the implied index on this radical is a 2. So anything underneath the radical that has a 2 for an exponent, we can pull it out of the radical. So we'll pull the 5 out of the radical, and then we'll pull the z out of the radical, and the 3 is left underneath the radical. And again, for the rest of the problems in this chapter, we'll see that the instructions tell us to assume that all variables are greater than or equal to 0. So when we see those instructions, we don't have to put absolute value bars around our variable. Let's try problem number 12 here. And from now on, I'm going to use this condensed notation. To start, I'm going to just move this coefficient to the side. We don't need to worry about it for now. Then, since the index here is a 4, we're looking for perfect fourths. First, we ask ourselves, is 128 a perfect fourth? It is not, because no whole number raised to the 4th power gives us 128. So since 128 is not a perfect fourth, we have to find the largest perfect fourth that multiplies evenly into 128. Let's look at our chart here. 16 is the largest perfect fourth that multiplies evenly into 128. So we need to rewrite 128 as 16 times some number. And if you take 128 divided by 16, you get 8. So that means that 16 times 8 gives us 128. Next, we're going to look at the variable. And again, the first question we ask ourselves is x to the 4th a perfect fourth? It is. We can see that because it's already written as some quantity to the 4th. Now, if we use the condensed notation, we're not going to break this apart into separate radicals. Instead, since our index is a 4, anything underneath the radical that's a perfect 4th power, we need to write it as some quantity to the 4th. 16 can be written as 2 to the 4th. 8 was just the leftover after pulling out the largest perfect fourth, 16, so we'll just bring down the 8. And then this perfect fourth is already perfectly written as some quantity to the 4th. So we're going to leave x to the 4th as is. Now we're going to pull those quantities out of the radical. First, let's pull this 2 out of the radical, and that will leave us with 2 outside of the radical. And notice when you pull this out of the radical, if there's already a coefficient, we multiply it by the existing coefficient. And then we'll pull the x out of the radical, and that will leave us with x outside of the radical. And now that we've pulled these red quantities out of the radical, all that we're left with underneath the radical is 8. Now be very careful. A very easy mistake is to forget to write the index on your radical. If the index is a square, you do not have to write the index. But if the index is anything other than a square, you have to write it. So here the index is a 4. Make sure you don't forget to put that index on your radical. And then for our final answer, 3 times 2 will give us 6, so we'll have 6x, 4th root of 8. Now again, for the rest of the problems in Chapter 6, the instructions will tell us that we can assume that all variables are greater than or equal to 0. So notice here when we pulled the x out of the radical, we didn't need to worry about using absolute value bars because we were told that we can assume that x is positive anyway. Let's pretend for a minute that we were not told that the variables are greater than or equal to 0. So if we just focus on the 4th root of x to the 4th, since the index matches the exponent, they're inverse operations and they cancel, but remember that when this is even, you need to use absolute value bars. So if we weren't assuming that all of the variables were greater than or equal to 0, then we would put absolute value bars around this x. But again, for all of the problems that we will see throughout the rest of the chapter, the instructions will say that we can assume that all variables are greater than or equal to 0. So we won't have to use absolute value bars. Let's take a look at problem number 13. The index is a 3, so that means we're looking for perfect cubes. First, let's focus on negative 27. Is negative 27 a perfect cube? Yes, it is. Negative 27 is a perfect cube because we can write negative 27 as negative 3 cubed. Then let's look at the variable. Is p cubed a perfect cube? Yes, because it's already perfectly written as some quantity cubed. Now, the index here is a 3, and we've identified the perfect cubes. So now anything underneath the radical that has a 3 for an exponent can be pulled out of the radical. So let's pull the negative 3 out of the radical, and then let's pull out the p. Now, if there's nothing left inside the radical, we don't need the radical anymore. So our final answer here is negative 3p. Now, notice on this page, all of our variables were perfect powers. Here, since this was a square root, we were looking for perfect squares. And conveniently, our variable was z squared. Here, we had a 4th root, and conveniently, our variable was a perfect 4th. Here, we had a cubed root, and conveniently our variable was p cubed. But what if your variable isn't a perfect power? For example, what if you had a square root, but instead of having z squared, you had z to the 7th? How do you simplify that? We're going to learn that on the next few pages. On page 2, we made a list of numbers that were perfect squares, perfect cubes, and perfect 4th powers. Now we're going to write a similar list, but this list is going to be examples of variables that are perfect squares, cubes, and 4ths. So the most basic perfect square would be x squared. And again, a perfect square is any quantity that can be rewritten as some quantity squared. The next perfect square would be x to the 4th. And x to the 4th is a perfect square because it can be written as some quantity squared. Let's see, what do we have to square to get x to the 4th? Well, if we remember, our rules of exponents tell us that when you raise a power to a power, you multiply. So it looks like we'd have to put a 2 here because 2 times 2 will give us 4. The next perfect square would be x to the 6th. X to the 6th is a perfect square because we can write it as some quantity squared. What do we have to square to get x to the 6th? Well, let's see here. What times 2 gives us 6? That would be 3. So that means that when we take x cubed and square it, we get x to the 6th. The next perfect square would be x to the 8th. And x to the 8th is a perfect square because we can write it as some quantity squared. Let's see. X to the 4th squared will give us x to the 8th because 4 times 2 gives us 8. And I've continued filling out this list to show you several more examples of perfect squares. Next, let's list some examples of perfect cubes that involve variables. The most basic perfect cube would be x cubed. The next perfect cube would be x to the 6th. X to the 6th is a perfect cube because it can be written as some quantity cubed. Now, what cubed gives us x to the 6th? Well, Again, our rule of exponents says that when we raise an exponent to an exponent, we multiply. So this exponent must be a 2, because 2 times 3 gives us 6. The next perfect cube would be x to the ninth, and x to the ninth is a perfect cube because we can write it as some quantity cubed. And let's see, x cubed would give us x to the ninth, since 3 times 3 is equal to 9. And I've continued listing several more examples of perfect cubes. Last, let's list examples of variables that are perfect fourth powers. The most basic would be x to the fourth, the next would be x to the eighth, and x to the eighth is a perfect fourth power because we can write it as some quantity to the fourth. And let's see, what would we have to raise to the fourth to get x to the eighth? Well, it must be x squared, since 2 times 4 gives us 8. And I've listed a few more examples of perfect fourth powers. Now, if you look closely, you'll find a pattern here, and this pattern makes it really easy to identify variables that are perfect squares, perfect cubes, or perfect fourth powers. Let's examine all of the exponents on our perfect squares. We've got 2, 4, 6, 8, 10, 12, and so on. Notice, for variables that are perfect squares, all of the exponents are multiples of 2. So if you have a variable and its exponent is a multiple of 2, you'll know that it's a perfect square. Next, let's examine the exponents on our perfect cubes. We've got 3, 6, 9, 12, and so on. For variables that are perfect cubes, the exponents are always multiples of 3. So if you have a variable and its exponent is a multiple of 3, you'll know that it's a perfect cube. Lastly, for our perfect fourth powers, all of the exponents are multiples of 4. So if you have a variable and its exponent is a multiple of 4, you'll know that that variable is a perfect fourth power. Let's look at these two examples. Again, we're asked to simplify, and again, the instructions say assume all variables are greater than 0. That just tells us that we don't have to worry about using absolute value bars. And first, we need to recognize that this is a square root. So that means that we're looking for perfect squares. First, let's look at 18. And we need to ask ourselves, is 18 a perfect square? It is not, because no whole number squared gives us 18. So since 18 is not a perfect square, we need to find the largest perfect square that multiplies evenly into 18. If you look back at our chart of numbers that are perfect squares, you'll find that the largest perfect square that multiplies into 18 is 9. So we're going to rewrite 18 as 9 times 2. Next, let's look at the variable. Since this is a square root, we'll ask ourselves, is x to the 8th a perfect square? There's a few different ways you can answer that question. You can either just look at our list of perfect squares here and see that x to the 8th is on the list. So that means that x to the 8th is a perfect square. Or if you don't have this list in front of you, remember that if you have a perfect square, its exponent will be a multiple of 2. This exponent 8 is a multiple of 2, so that means that x to the 8th must be a perfect square. So since x to the 8th is a perfect square, I'm going to write it in red here. The next step is anything that's a perfect square, in red here, we need to write as some quantity squared. So we can write 9 as 3 squared. 2 was just the leftover after we pulled out the largest perfect square 9, so I'll just carry down the 2. And then x to the 8th is a perfect square, so we need to write it as some quantity squared. We can either just look at our list up here and it tells us how to do that, or we can think through this logically, because we know that when you raise an exponent to an exponent, we multiply. So we know that this must be a 4 because 4 times 2 gives us 8. Now, since this is a square root, anything underneath the radical that has a 2 for an exponent can be pulled out of the radical. So let's pull this 3 out of the radical, and then let's pull this x to the 4th out of the radical. Now keep in mind, this square root cancels the square on the x to the 4th, but this 4 stays. So we'll be left with x to the 4th. And then all that we're left with underneath the radical is the 2. And this is our final fully simplified answer. Let's take a look at this next example. Now first we have to notice that the index is a 3. That means we're looking for perfect cubes. 54 is not a perfect cube. So we have to find the largest perfect cube that multiplies evenly into 54. You'll find that 27 is the largest perfect cube that multiplies evenly into 54. So we're going to rewrite 54 as 27 times 2. Next, we'll look at the variable x to the 6th, and we need to ask ourselves, is x to the 6th a perfect cube? Yes, it is, and there's two ways you can know that. You can either look at our list here of perfect cubes, and you'll see that x to the 6th is on that list. Or we can always identify variables that are perfect cubes because their exponents will be a multiple of 3. 6 is a multiple of 3, so that means that this is a perfect cube. So for now, since it's a perfect cube, I'm going to put it in red. Now that we've identified our perfect cubes, anything that's a perfect cube, we want to write it as some quantity cubed. 27 can be written as 3 cubed. X to the 6th is a perfect cube, so we need to write it as some quantity cubed. You could just look at the list up here and it will tell you how, or we can think through this logically. Let's see. We'd have to put a 2 here because 2 times 3 gives us 6. Now that we've written all of our perfect cubes as some quantity cubed, anything underneath the radical that has a 3 for an exponent can be pulled out of the radical. So we'll pull this 3 out of the radical, and that will leave us with this coefficient 2 times the 3 that we're pulling out, and then we'll pull this x squared out of the radical. Underneath the radical, we're just left with 2. Last step is just to simplify. 2 times 3 will give us 6x squared cubed root of 2. Now, notice in these examples, here we had a square root, and our variable was a perfect square. We could write it as some quantity squared. Here we had a cubed root, and our variable was a perfect cube. We could write it as some quantity cubed. But what if you have a square root, but your variable is not a perfect square? Or what if you have a cubed root, but your variable is not a perfect cube? How do we simplify those types of problems? We'll look at that next. So again, we're asked to simplify here, and we'll be able to assume that all variables are greater than 0, so we don't have to worry about using absolute value bars. So let's see. Here, this is a cubed root, so that means that we're looking for perfect cubes. So the first question we need to ask ourselves is x to the 5th a perfect cube? If we look back at this list, we'll see that x to the 5th is not in our list of perfect cubes. Even if we don't have this list in front of us, we know that x to the 5th is not a perfect cube because the exponent 5 is not a multiple of 3. So x to the 5th is not a perfect cube. So therefore, we need to find the largest perfect cube that multiplies evenly into x to the 5th. There's a really nice, easy trick you can use. If you're looking for the largest perfect cube that multiplies evenly into x to the 5th, you just need to find the exponent as close to 5 as you can get, but it has to be less than 5. The exponent on this list that's as close to 5 as we can get, but less than 5 would be x cubed. So that's our answer. X cubed is the largest perfect cube that multiplies evenly into x to the 5th. So now we need to rewrite x to the 5th as x cubed times some quantity. So what do we have to multiply x cubed by to get x to the 5th? Well, let's again remember our laws of exponents. When you multiply two quantities with the same base, you add their exponents. So this exponent needs to be a 2 because 3 plus 2 gives us 5. So we've rewritten x to the 5th as x cubed times x squared because x cubed was the largest perfect cube that multiplied into x to the 5th. Now, since the index is a 3, anything underneath the radical that has a 3 for an exponent can be pulled out of the radical. So we'll pull this x out of the radical. This does not have a 3 for an exponent, so it stays underneath the radical. Let's take a look at another example. Here the index is an implied 2, so we're going to look for perfect squares. First we need to ask ourselves, is z to the 13th a perfect square? If we look at our list of perfect squares here, z to the 13th would not be on this list. We also know that z to the 13th is not a perfect square because the exponent 13 is not a multiple of 2. So z to the 13th is not a perfect square. So we need to find the largest perfect square that multiplies evenly into z to the 13th. Let's use our trick. So let's look at our list of perfect squares. And if we're looking for the largest perfect square that multiplies evenly into z to the 13th, we need to find the exponent as close to 13 as we can get, but it has to be less than 13. The exponent on this list that's as close to 13 as we can get, but less than 13 would be 12. So that means that z to the 12th is the largest perfect square that multiplies evenly into z to the 13th. So now that we've identified our largest perfect square, we need to rewrite z to the 13th as z to the 12th times some quantity. Let's see. Remember when you multiply two quantities with the same base, you add their exponents. So this exponent must be a 1 because 12 plus 1 will give us 13. Now we need to rewrite our perfect square as some quantity squared. To rewrite z to the 12th as some quantity squared, let's see. We'll put a z here, and then this must be a 6 because 6 times 2 gives us 12. And then we'll bring down our z. Now that we've rewritten our perfect square as some quantity squared, now we can pull it out of the radical. So we'll pull out the z to the 6th, and then the z stays underneath the radical. Let's take a look at this example here. Notice here this is a fourth root, so that means that we're going to be looking for perfect fourth powers. I'm going to start by focusing on the 16. Is 16 a perfect fourth? It is, because 16 can be written as 2 to the 4th. So for now, since 16 is a perfect fourth, I'm just going to put it in red, because for now I'm just identifying all of the perfect fourths. Next, I'm going to focus on x to the 5th. Is x to the 5th a perfect fourth? It is not. We know it's not because 5 is not a multiple of 4. So since x to the 5th is not a perfect fourth, we have to find the largest perfect fourth that multiplies evenly into x to the 5th. If we look at our list of perfect fourths, we just need to find the exponent as close to 5 as we can get, but it has to be less than 5. That would be 4. So the largest perfect fourth power that multiplies evenly into x to the 5th will be x to the 4th. So we need to rewrite x to the 5th as x to the 4th times some quantity. And let's see, x to the 4th times x is equivalent to x to the 5th, since when we add their exponents, 4 plus 1, we get 5. Next, let's focus on y to the 11th. Is y to the 11th a perfect fourth? It is not, and we know that because 11 is not a multiple of 4. So we need to find the largest perfect fourth that multiplies evenly into y to the 11th. We need to find the exponent as close to 11 as we can get, but it has to be less than 11. That would be y to the 8th. So since y to the 8th is the largest perfect fourth power that multiplies evenly into y to the 11th, we'll rewrite y to the 11th as y to the 8th times some quantity. And let's see, y to the 8th times y cubed will give us y to the 11th, since when we add their exponents, 8 plus 3, we get 11. We next need to rewrite each of these perfect fourths as some quantity to the 4th. 16 can be written as 2 to the 4th. Our next perfect fourth is x to the 4th, but that's already perfectly written as some quantity to the 4th, so we'll leave it as is, and we'll bring down the x. Y to the 8th is in red, it's a perfect fourth, so we need to write it as some quantity to the 4th. Let's see, this must be y squared to the 4th because 2 times 4 gives us 8. And y cubed was just the leftover after we pulled out the largest perfect fourth, y to the 8th, so we'll just bring down the y cubed. Now, anything underneath the radical that has a 4 for an exponent can be pulled out of the radical. So let's pull the 2 out of the radical, and we'll pull this x out of the radical, and we'll pull this y squared out of the radical. All that we're left with underneath the 4th root is x and y cubed. Let's take a look at these next two examples. Now the instructions say to use the product property of radicals to multiply and then to simplify. Since we're multiplying two cubed roots, the product property of radicals says that we can combine that multiplication underneath one cubed root symbol. So we're going to take 6a cubed b to the 5th and multiply by 18a squared b to the 7th. Now remember, when you're multiplying a bunch of different quantities together, we multiply the like quantities. So we'll multiply the numbers. 6 times 18 gives us 108. And if we take a cubed times a squared, we keep the base, which is a, and we add the exponents. So 3 plus 2 gives us 5. And then we'll multiply the b's. So we'll take b to the 5th times b to the 7th. We keep the base, b, and we add the exponents. 5 plus 7 will give us 12. Now we've used the product property of radicals to multiply. Next, we need to simplify. The index here is a 3, so that means we're looking for perfect cubes. First, let's look at 108. 108 is not a perfect cube. If you type the cubed root of 108 into your calculator, you'll get an ugly decimal. So since 108 is not a perfect cube, we need to find the largest perfect cube that multiplies evenly into 108. If we look at our list of perfect cubes, you'll find that the largest perfect cube that multiplies evenly into 108 is 27. So let's rewrite 108 as 27 times some number. 27 times 4 is equivalent to 108. Next, let's look at the a. And since the index is a 3, we need to ask ourselves, is a to the fifth a perfect cube? It is not, because for variables that are perfect cubes, their exponents will be multiples of 3, and 5 is not a multiple of 3. Let's look at our list of variables that are perfect cubes. And if we need to find the largest perfect cube that multiplies into a to the fifth, we need to find the exponent as close to 5 as we can possibly get, but it has to be less than 5. It looks like that would be a cubed. So since a cubed is the largest perfect cube that multiplies evenly into a to the fifth, we need to rewrite a to the fifth as a cubed times some quantity. And let's see, a cubed times a squared will give us a to the fifth. Since 3 plus 2, you get 5. Next, let's look at b to the 12th. Is b to the 12th the perfect cube? In fact, it is, because remember, for variables that are perfect cubes, their exponents will be a multiple of 3. And 12 is a multiple of 3, so this is a perfect cube. So for now, I'm just going to write b to the 12th in red, since we're putting all of our perfect cubes in red. Now, all of the perfect cubes need to be rewritten as some quantity cubed. We can rewrite 27 as 3 cubed. 4 was just a leftover, so we'll bring that down. A cubed is already perfectly written as some quantity cubed, so we'll leave it as a cubed, and then we'll bring down the leftover a squared. And now b to the 12th is a perfect cube, so we need to write it as some quantity cubed. Let's see, it looks like we'd have to put a 4, because 4 times 3 gives us 12. Now that we've written all of the perfect cubes as some quantity cubed, we need to pull those cubes out of the radical. First, let's pull out the 3, and that will leave us with this coefficient 5 times the 3 that we're pulling out. We'll pull out the a, and this also has a 3 for an exponent, so we need to pull that out of the radical. And that will leave us with b to the 4th outside of the radical. Let's see, we pulled out these pieces in red out of the radical, and that leaves us with, underneath the cubed root, 4a squared. And then we can simplify. 5 times 3 will give us 15a b to the 4th, cubed root of 4a squared. Let's take a look at this next example. First, we're going to use the product property of radicals to multiply. That will leave us with 18a to the 9th b to the 6th times 5a cubed b, all underneath the square root. Now remember, when you're multiplying a bunch of different quantities together, we multiply the like quantities. So let's take 18 times 5, which gives us 90. And then if we multiply a to the 9th times a cubed, we keep the base, which is a, and we add the exponents. 9 plus 3 gives us 12. And lastly, if we multiply b to the 6th times b, we keep the base, which is b, and add the exponents. 6 plus 1 will give us 7. Now that we've used the product property of radicals to multiply these two quantities underneath one radical symbol, we'll simplify. Since this is the square root, we're looking for perfect squares. First, we need to ask ourselves, is 90 a perfect square? It's not. If you take the square root of 90 on your calculator, you'll get an ugly decimal. So we need to find the largest perfect square that multiplies evenly into 90. 9 is the largest perfect square that multiplies evenly into 90. So let's rewrite 90 as 9 times 10. Next, let's look at our variable. We're looking for perfect squares since this is the square root. So first we ask ourselves, is a to the 12th a perfect square? Yes, it is, because 12 is a multiple of 2, so this is a perfect square. So for now, I'm just going to put a to the 12th in red since it's a perfect square, and I'm putting all perfect squares in red. Next, let's ask ourselves, is b to the 7th a perfect square? It is not, since 7 is not a multiple of 2. So we need to find the largest perfect square that multiplies evenly into b to the 7th. Let's look at our list of variables that are perfect squares. And to find the largest perfect square that multiplies evenly into b to the 7th, we need to find the exponent as close to 7 as we can possibly get, but it has to be less than 7. So it looks like our exponent would be 6. So the largest perfect square that multiplies evenly into b to the 7th will be b to the 6th. We need to rewrite b to the 7th as b to the 6th times some quantity. B to the 6th times b to the 1 will give us b to the 7th, since when we add their exponents, 6 plus 1 gives us 7. Now that we've identified all of our perfect squares in red here, we need to rewrite all of those perfect squares as some quantity squared. 9 can be written as 3 squared, and we'll bring down the 10. A to the 12th is a perfect square, so we need to write it as some quantity squared. And let's see, it looks like we would have to square a to the 6th, because 6 times 2 gives us 12. And b to the sixth is a perfect square, so we need to write b to the sixth as some quantity squared. Let's see, it looks like we'd have to square b cubed, since 3 times 2 gives us 6. And then we'll bring down our b. Now, since this is a square root, anything underneath the radical that has a 2 for an exponent can be pulled out of the radical. So we'll pull the 3 out of the radical, we'll pull a to the sixth out of the radical, and we'll pull b cubed out of the radical. All that we're left with underneath our square root is 10b. On the last page, we're going to learn one other important property of radicals. The quotient property of radicals says that when you divide two radicals that have the same index, you can combine that division underneath one radical symbol. The quotient property also works in the reverse direction. So if you're dividing two quantities underneath one radical, you can break that division apart into two separate radicals. So we don't yet know how to simplify radicals that involve fractions. But the quotient property of radicals can make this problem much easier to work with. The quotient property of radicals, if we go in this direction, says when you're dividing two quantities underneath one radical, you can break that apart into two separate radicals. So let's break this apart and write it as the square root of 12 divided by the square root of 49. To simplify the square root of 12, since we're dealing with square roots, we need to ask ourselves, is 12 a perfect square? It is not. So we need to find the largest perfect square that multiplies evenly into 12. You'll find that 4 is the largest perfect square that multiplies evenly into 12. So let's rewrite 12 as 4 times 3. Then let's look at the denominator. Is 49 a perfect square? It is. So the square root of 49 simplifies to the nice whole number 7. Now let's look back at the numerator. We can write 4 as 2 squared, and then we'll bring over the 3, and the denominator will stay as 7. And now we can pull the 2 out of the radical, and that will leave us with 2 square root of 3 over 7. Let's take a look at the next problem. If we use the quotient property of radicals, like we did up here, to break it apart into two separate radicals, that's going to make this a lot easier to work with. So I'm going to break this apart into the cubed root of negative 125 w cubed divided by the cubed root of 8. Since our index here is a 3, we're going to be looking for perfect cubes. If we look at the numerator here, is negative 125 a perfect cube? It is. We can rewrite negative 125 as negative 5 cubed. Then let's look at the variable, and let's ask ourselves, is w cubed a perfect cube? Yes, it is. And in fact, w cubed is already written as some quantity cubed. So we'll leave it as is, but we'll put it in red since it's a perfect cube. Then if we look at the denominator, first we ask ourselves, is 8 a perfect cube? And it is. We can rewrite 8 as 2 cubed. So now that we've identified all of the perfect cubes, since this is a cubed root, anything underneath the radical that has a 3 for an exponent can be pulled out of the radical. So in the numerator, we'll pull negative 5 out of the radical, and then we'll pull w out of the radical, and nothing is left underneath the radical, so we don't need the radical in the numerator anymore. And then in the denominator, we'll pull the 2 out of the radical, and again, there's nothing left underneath this radical after we pull the 2 out, so we don't need this radical anymore. Let's take a look at this last example. Now I'm going to show you two different methods for solving this problem. We'll start with a method that's very similar to what we did for these two problems. Notice for these two problems, we started with a quotient underneath a radical, and we broke that apart into two separate radicals. For this problem here, our problem is already broken up into two separate radicals. So for my first method, just like we did over here, I'm going to simplify the numerator and the denominator separately. To simplify this numerator, let's first look at 45. And since this is a square root, we want to ask ourselves, is 45 a perfect square? It is not. The largest perfect square that multiplies evenly into 45 is 9. So let's rewrite 45 as 9 times 5. Next, let's look at our variable. Is y to the fifth a perfect square? It is not, since 5 is not a multiple of 2. To find the largest perfect square that multiplies evenly into y to the fifth, we want to find the exponent as close to 5 as we can possibly get, but it has to be less than 5. That would be 4. So it looks like y to the fourth will be the largest perfect square that multiplies evenly into y to the fifth. So let's rewrite y to the fifth as y to the fourth times some quantity. And let's see, y to the fourth times y will give us y to the fifth, since when we add the exponents 4 plus 1, we get 5. Next, let's look at the denominator here. First, we want to ask ourselves, is 5 a perfect square? It is not. And if we try to find the largest perfect square that multiplies evenly into 5, you'll find that the largest perfect square is 1. So that means we can't simplify the square root of 5 any further. Same with y. Y is not a perfect square, and there are no perfect squares that multiply evenly into y. So that means we leave this denominator as is. It cannot be simplified any further. Next, anything in red, anything that's a perfect square here, we need to write it as some quantities squared. We can rewrite 9 as 3 squared. 5 was just a leftover, so we'll bring that down. And let's see, y squared will give us y to the fourth, since 2 times 2 gives us 4. And y was just a leftover, so we'll bring that down. And then we said the denominator cannot be simplified any further. Now we'll pull the 3 out of the radical, and we'll pull the y squared out of the radical. Now this square root cancels one of the squares, but not both. So we're left with just y squared. And then underneath the radical, we're left with 5 and y. Now notice here, we have the square root of 5y in the numerator and the square root of 5y in the denominator. So we can cancel that out, and that leaves us with our final answer of 3y squared. Let's take a look at another shorter method we could have used for this problem. Notice for this problem here, if you take 12 divided by 49, you get an ugly decimal. Same thing here, if you take negative 25 divided by 8, you get an ugly decimal. But this is different. 45 divided by 5 gives us a nice whole number. For this problem, an alternative approach would be to use this quotient property of radicals and to combine this division underneath one square root. So we're going to draw a square root, and then underneath the square root, we'll write 45y to the fifth divided by 5y. The reason this is helpful for this particular problem is because 45 divided by 5 gives us a nice whole number 9. And remember, when you divide two quantities with the same base, you keep the base and subtract the exponents. So 5 minus 1 will give us 4. So by combining this division underneath one radical, we were able to simplify this problem quite a bit. Now let's simplify this further. First, let's ask ourselves, is 9 a perfect square? And it is. We can write 9 as 3 squared. Then let's ask ourselves, is y to the fourth a perfect square? And it is. We know that because 4 is a multiple of 2. So since y to the fourth is a perfect square, we want to write it as some quantities squared. And let's see, if we take y squared and square it, we'll get y to the fourth, since 2 times 2 gives us 4. Now we'll pull out the 3, and we'll pull out the y squared. And notice using method 2, we got the exact same answer that we did using method 1.